Today we are starting with the actual inference for linear regression. We're going to talk about some things and stuff. Let's see how it goes. What is inference for linear regression? Inference, I would argue, has been kind of intuitive up to this point. Which again, to clarify, that doesn't mean it's been easy, but we take a sample, we say, based on the sample, what can we say about the population? Z-test draws sample proportions. We use those to make inferences about population proportions. And therefore, and there we go. Even chi-square are fairly straightforward. If we remember, we're just comparing distributions to see if they match up with what we'd expect. It's pretty straightforward. Inference for linear regression might not immediately make sense. Like, what is it talking about if we're looking at a scatter plot and a regression equation? We're going to do some inference on that. What is that even referring to? So luckily, we will I'm going to lay out right now exactly what we're studying. We're going to be looking at confidence intervals to estimate the true slope of a regression line. So I will tell you this, inference on linear regression is always related to the slope. We don't care about the y-intercept. So we can just completely ignore that. So we're talking about the slope. What is the true slope of a regression line? Because if we took a different sample, let me give you a quick overview real quick. Here is your sample. Okay, and I get this regression line, and my slope is whatever. Slope number one is this. But now, let me clear this. I've got a different sample now, which looks like this. This might not look any different. Here's my other one. So my first one might have looked like this, the second one like this, and I took another sample, it might be right here. So what is the true population slope? Because I could get a lot of different slopes based on the sample. So the confidence interval is basically saying, what is the estimate of the true population slope if we had all the information? All right, and likewise, we could say this. If we're going to do a hypothesis test, we're going to start with the assumption that there is no relationship between these two variables. So I might have the null hypothesis being that there is no relationship at all between these two, and here's my regression slope. But maybe our sample looks like this. Keep drawing positive ones, but whatever, it could be negative. And so what is the probability that I would get a slope that looks like that if there really was no association between these two variables? And then we can figure it out with our p-values, and we can determine, oh, well, this is far enough away from a zero slope that we can determine that there really is an association between the two variables. All right, we're not getting into all of this today. The inference will be tomorrow, but that's essentially what we're talking about when we're talking about inference for regression. Okay. So we will look at confidence intervals. So we don't care about, okay. Well, let me go back. And I already mentioned that. We don't care about the y-intercept. We're only dealing with the slope of the regression line. Okay, here we're going to run through a few things real quick. These are the conditions. Now we've gotten pretty familiar with our conditions by now. So 10%, random, and normal. But we have some other things that we need to consider when it's inference for linear regression. First of all, we have to make sure that our scatter plot is actually linear. So if you remember when we were doing this before, I asked you to review Unit 3. We had DUFs. And this is how we can describe the relationships. Like here, we would say this is a negative. That's your direction. The unusual features, I don't see any outliers or anything. The form of this is linear. And the strength, that's where we can come up with our correlation coefficient based on what we're seeing. So I might say that's a 0.7. Sure, why not? Seems good enough. So when we're checking for conditions, we want to first of all make that this is linear. And so these two are good for inference. These two are not. We want to make sure there is equal variance. This is another one of these conditions that we talked about in the past. And the condition here is that we don't want to see the scatter widening or narrowing across the regression line. We want to see it pretty constantly scattered. And of course, you can imagine the reason for this is that we're going to get much more accurate results here than we will here. And if we try to project this out into the future, you know, who's to say this doesn't like widen out like this? And then you get to that far, and this prediction is pretty worthless. So again, extrapolating on its own is not very good because we don't really know that this trend is going to continue, but we probably feel a little better with a prediction from this model right here. So equal variance and normal. This is something that, this is a real blast from the past right here. This is called a normal probability plot. And essentially what this is comparing is the theoretical quartiles. Basically, if you had 100, let's say this is 100 data points. If you had 100 data points and it was normally, and it was a normal distribution, a perfectly normal distribution, what value would your lowest one be? What value would your next one be? And so on. These are theoretical quantities in the vertical direction. Horizontally, it's your actual results. So if your actual observations match up with the theoretical ones, then you're going to get this perfectly, well, this very close to straight line right here. So this is what you're looking for. You don't want to see a curve like this or anything. So there we are. So that's a good normal probability plot. Independent, random, and there we are. Now we have this nice, what's the word I'm looking for? Acronym, mnemonic. So that can remind us of the conditions for conditions for inference for linear regression, LINER. Two of them are the same. Well, actually, three of them are the same: independent, normal, and random. But linear and equal variance are going to be the new conditions we need to check for. This is something you can come back to. It's in the presentation. You can find this PDF. There's the reference posters that are in Canvas. You can find those and it'll have this as well. Now, if this does seem like a lot to remember, linear regression is a unit. I think I mentioned this before, but this is one that if stats teachers are running low on time, they will frequently just skip it completely. So if this is like, oh my gosh, we're throwing the wrench in the machine and this is making it really complicated, don't worry, you're unlikely to see too much on this topic. Yeah. Yeah. Yeah.
How will the test reflect that?
The unit test will reflect it in the sense that it probably won't count for as much. But it's all going to be a bunch of questions related to linear regression. And so I will say this, it is likely you're going to see a question related to linear regression, inference for linear regression on the AP test, those of you taking it. But it's unlikely you're going to see more than 2. It's unlikely you're going to have an FRQ related to it.
No.
Yeah, it is possible and it has happened. But yeah, well, I'll also show you that mathematically this is maybe the easiest math stuff that we have to do. Conceptually, huh? Yeah, yeah, and conceptually, this can be a little bit, well, confusing. I don't know, but mathematically, they do a lot of the work for you, and we're going to get to that to some degree today. So here are some possibilities. You might have multiple choice questions asking you to investigate whether conditions have been met. But you can kind of think through it. If you can remember that you need to have equal variance in your residuals and you need to have a linear form, then you can kind of add those to what you know about your conditions for inference anyway. Okay. Now, this might not make a lot of sense right now. As far as FRQs go, you will get, I can guarantee you, if they give you an FRQ with a question related to this unit, they're going to give you a computer printout. We've seen those before, but they're going to come back and we're going to investigate what those numbers mean. And the investigative task is FRQ number 6. I will go ahead and say there's about a 0% chance your investigative task will relate to linear regression inference. So I guess what I'm trying to say is don't stress about this stuff too much. So as a reminder, kind of the stuff we've looked at up until now, we have a population parameter that has its own notation, and we have a sample statistic that has its notation. And you're familiar with these by now. So when we're looking at slope, we have the same thing. Your population parameter is called beta, and your sample statistic is just B. Now we can see why we always refer to our slope as B instead of A or M or anything else. So pretty straightforward. So now let's talk about confidence intervals. Maybe I'll pause right here. Are there questions that you guys have? Okay. This generic formula for a confidence interval you're familiar with, and that doesn't change. But now we need to remember, now we want to look at what, okay, this is just a side note that because linear regression inference uses means, we're going to use T star as our critical value. We're going to kind of work through what this means. Okay, so because we're doing it, and I kind of mentioned at the beginning, our confidence interval is a confidence interval saying, what is the true slope found in the population? So we're going to start with our sample slope, and then we're going to figure out what the standard error of the slope is going to be and multiply it by a critical value based on whatever confidence level we're shooting for. Okay. We'll come back to that. Here, this is from the AP formula sheet. You can see what the standard error formula is for linear regression. And this S right here is the same as S sub E. And that is the standard deviation of the residuals. So just as a reminder, let me just kind of visually explain what's going on with this. Boom, boom. All right, so here is your regression. We're unit 3 stuff. We found a regression line. It's been plotted. I'm going to draw a regression line, the regression plot right here. So now I've got maybe some stuff that looks like this. Boom, boom, boom. Boom, boom. I'm actually trying to make this look the same. All right, so I probably didn't do very well with this, but it doesn't matter. So if you can see those dots, they're kind of small. The standard error is the average distance. Let me try that again. The average distance that an error, that a residual is from the regression line. So you're gonna have some that are positive and some that are negative, and we can create a distribution of our residuals, which all the residuals should follow this, and then we can figure out what's the average distance away. And so we're going to have a line right here and here that represents where the average residual is going to fall. So that's what the S at the top right here means. Now the S sub X, what is the standard deviation of just your X values? So every one of these data points has an X value, right? And this comes from a data set. And we just want to figure out what is the standard deviation of this. So this, if I just looked at the one variable that represents the X value, it's going to have its own mean. So my X bar might live right here. And then from there, if I had a bunch of data points, I might even have a distribution that looks like this, and I can figure out how much does the X vary from the mean. And you can see the calculations for that right here and here. And then we, of course, we divide by the square root of our sample size. We just do 1 less. That's just a correction that's made. Honestly, it doesn't matter why. I can't even tell you. I could explain why. But we're essentially saying it's the change in our y value from what we'd expect over the change in our x times the square root of the population, of the sample size, rather. Right. So I want you to focus on this for a second to realize that this is complicated, right? And I said at the close to the beginning that this is kind of the least mathematically involved stuff we have to do, and it's already looking pretty complicated. If we wanted to find this, we'd first of all need to find this calculation separately, and then this calculation separately. And anytime you see a sigma, if you have 100 data points, you have to calculate each one of these individually. All right, so technology handles this for us, and we never do this by hand. If anything, you might need to show your formula to show that here's the work that's being done, first of all. But you might need to refer to this if they ask you a conceptual question. They might say, how would changing the standard deviation in your x value affect the size of your confidence interval? All right. Now, if we answer that one, since this is our standard error, then since this is inversely related, increasing your standard deviation of your x value is going to decrease the width of your confidence interval. All right, but I'm not getting into that so much. I'm trying not to make this seem super complicated, but I'm going to pause there and ask if there are questions coming up. Okay. Well, this is the specific formula that we can use. This is just everything plugged in. All right. And the degrees of freedom is just going to be the sample size minus 2. Remember, we have 2 variables that we're dealing with, our explanatory and our response variable. So basically we're going to subtract, because we have 2 variables, we're going to subtract 2 from our sample size. Okay, now let me go ahead and copy this formula over. So we've got this one, and I'm just going to bring this over. You know what? I don't even want to do this problem. You know what? We will. And I'll explain why. You will never have to do a problem like this on the AP test. You won't even have to do a problem like this on the test in class. But this is good review because it's going to run through a lot of concepts. So we'll just do this real quick. So my formula is b plus or minus t star. And then that's going to be times s sub e divided by s sub x and the square root of n minus 1. All right. I encourage you to kind of write this stuff down or take a screenshot at the end, whatever you need to do to learn this. So we've got the ages of cars. We've got the advertised price. So obviously the older a car gets, the less it should cost. And we can see that that's generally true, but we're going to make sure that we're going to look at what the possible slopes could be, and then we'll interpret that. So the first thing that we can do is, using our calculator, we can create a scatter plot for this. So maybe list 1 could be your age in years, and list 2 could be the price. Make sure they match up, and we can all plug those in. So if you succeeded in getting this done, then I'm going to put this up on the screen. You should have a scatter plot that looks like this. And the question, if we're talking about, is it appropriate to continue? We need to know, first of all, if it's random, if it's a small sample size, and if the selections are independent. I think we could argue that. The things we need to consider now is, do we have equal variance and do we have a linear form? Yeah, it sure looks it looks linear to me, so that's not a problem. We're technically not seeing the results of the residual. It's not worth it for us to go and find that. If you're ever expected to determine if it has equal variance, they're going to give you the residual plot. Okay. We're definitely doing a lot of Unit 3 review as part of this problem. So now what we want to do is actually find the linear, the equation of the regression line. So we kind of answered part B. I'm not writing it out. Do we think it's appropriate? Yeah, I think it's appropriate. And I think we could all eventually understand that it is. If you have questions on that part, let me know. The regression equation you can find by going to stat and then calc. And if you go down to option 8, that's linear regression A plus BX. You just pick list 1 and list 2 and calculate. So when I did that, I got this printout. Okay. So we will want to have reference to that. You know, we might do this entire problem and we're going to see that if we wanted to calculate this, even using the calculator, it's very time consuming. So it's equal to 14,285.90 minus 959.05 times x. So to interpret this regression equation, we're saying that at 0 years old, this car is worth about 14,285. But every year, it loses about $1,000 in value. So by the time it's 14 years old, it's not worth anything. All right, so that's in context what this regression equation means. And now what we want to do is, now it says check the residuals. We're not going to check the residuals. Okay, I'm going to skip this part. But we do have the regression equation. So now what we want to do is we want to create a 95% confidence interval for the slope of a regression line and explain what your interval means in context. So I say this a lot, but I want to remind you, the AP test is designed so you can take it without a calculator, theoretically. So with these calculations, it requires a calculator to get this done in a timely manner. So we're going to be realizing that this is not something you'd have to do on the test. So this right here represents B. So I'm going to start with that, negative 959.05. Plus or minus, I want to find out what the true population slope might be. According to my sample, we're going to lose about $960 a year. But maybe the population is more or less than that. So T star, we'll skip that for now, just leave it blank. And then the S sub E, well, we don't know that one yet. I'm going to leave it blank. S sub X, we don't have that, or we don't have it yet. N is, we got 15 data points. So it's going to be 14 right here. Square root of 14. So again, to do this the long way, the standard deviation of your residuals, when you run a regression analysis, it automatically creates residuals for you. Okay. So let me see. I want to make sure I'm about to say the right thing here. Sorry, I'm running through and Where are my residuals? See, my hope is to do this the long way, just so you can have appreciation for it. I can't seem to find my residuals. They're not where I expected them to be. Store. Okay. You know what? We might just have to skip this. Okay, there it is. I found it. Is it even worth it? Now we have to ask ourselves that question. Okay, I'm just going to show you this. I'm not going to make you guys do this individually. It took me a while to find this anyway. So to get the standard deviation of our residuals, which is going to be S sub E, that's what goes right here. What I have to do is do our one variable stats. And there's a way of accessing your residuals. And I just did that right here. Don't worry about, if you want to know how I found it, you have to go into your list menu and get that. But just to, I'm getting an error. Screw this. Forget it. It's not worth our time. Okay. We could calculate the residuals, but I'm not going to worry about it. Okay. So anyways, if I knew that number, I don't know what it is, but if I knew it, then I could easily find my standard deviation for my X values, which is basically just take this list, run one variable stats on it, and get that number. I could do that for sure. So it's going to be list one. The standard deviation there is 3.378. Okay. So at this point, we'll just look at the T-star just as a review of some concepts. And then beyond that, I'm going to skip past this problem, okay? Because we're never going to do anything like this. My degrees of freedom here, if there are 15 values, and my degree of freedom is 15 minus 2, then I'm going to have 13 degrees of freedom with 95% confidence level. So I can just go to 13 right here, come over until I see my 95%. And that gives me 2.160. All right. So assuming we could get the standard error of the residuals right now, and there's a more time-consuming way of doing that if we want to put more effort into it. But assuming that, we're going to get this number, and we can just finish calculating from there. It's going to give us a range. So if I pretend that we came up with this, this might go from negative 900 at the low end, or that would be the high end actually, negative 900 at the high end, down to negative 1020 at the low end. So we're not sure exactly how much value is lost every year, but it's going to, with 95% confidence, we can say it's going to lose somewhere between $900 and $1,020. Okay. You guys feel like your brain is thoroughly fried, or are you following along with this? Okay. And I said at the beginning that I was almost going to skip this problem because we don't ever do it this way, not in AP stats. Okay. Even in the real world, you let technology do this for you even more than we're talking about. This is what it looks like more frequently. When you get to college and you do another stats class, which will be true for the vast majority of you, you will be using statistics programs that run analysis for you and just give you a printout. And so it's a lot more about interpreting the numbers you see rather than knowing how to use a calculator, because you probably won't even use a TA 84 or anything like this in a stats class unless you want to. So let's look at this. They give us a few things to work with, but they give us the intercept and our verbal. This is comparing the verbal and math scores of an SAT. So the verbal, we can see that for every point in verbal, we would expect to get 0.675 points in math if we're making this prediction. The standard error is found right here. This is what we would have calculated, but it automatically gives it to us. And then we get our t ratio, which is our t value, and then our p value. All right, we're not doing any stats hypothesis testing today, so we'll jump back into that tomorrow. But we are looking at this right here, b plus or minus the t star times the standard error of our residuals over the standard error of r. Standard error of our x values divided by, or times n minus 1, square root of n minus 1. Okay. And they give us some numbers here. Let's make sure this turns out right. This is the number we should be calculating. If we do our calculation right, that is exactly the same number. Okay? We can actually skip that entire calculation. I just spent a good amount of time trying to go through it on the previous problem and failed at it because I couldn't get the standard error of my residuals. They already calculated it for me. If we needed to calculate this by hand, and I hope I'm about to do this part right. Let's see, hopefully this turns out right. The standard error of our slope is going to be, we have this S given right here. That is the standard error of our residuals. So I'm going to put 71.75. All right. So that number is probably going to be given to you. The other one that we need might not be, because you don't always see this part of the printout. Okay. So in here, it gives me the standard deviation of 99.5199 for verbal. That's since verbal is my X value, the standard deviation of my X value is given right there, 99.5199. Times the square root. The sample size here is given lots of different places. We can see 162, 162. It even says, no, it doesn't say it up there. So it's going to be 162 minus 1. That's 161. Let's plug that all in. Make sure we should get 0.0568. Let's see. This is live and being recorded, so I can add to my errors of the day. Aha! I just plugged it in. I don't know if anyone else did the calculation as well. So there it is, 0.0568. All right. So they give us kind of too much information almost in this printout. It gave us the standard deviation of X. It gives us standard deviation of Y, which we don't use anyway. It gives, unless there is a different type of problem. It gives us the standard deviation of our error, and it gives us a standard deviation of our slope. And since this is what we're trying to solve for in the first place, we're good to go. All right, so our slope is right here. This is B. So it's going to be 0.675 plus or minus my T star, which I'll leave blank for right now, times 0.0568. And I think when we're doing our hypothesis testing tomorrow, I'm just going to skip straight to using this printout, and we're going to skip past all the more confusing aspects of it. All right, now the T star on this, my degree of freedom, because there's 162 in my count, it's going to be n minus 2, which would give me 160 degrees of freedom. Now with this, we just want to go to the next lowest. So 100 would be the next lowest with a 90% confidence level with 100 degrees of freedom from this table. It would be 1.660. So my T star is 1.660. And I'm going to pause there. Are there questions on how I got any of these values? Okay. So 1.660. Now we can just calculate that and get the regression, or sorry, the confidence interval from this. So I'll go ahead and pause this. You guys can calculate it. And again, think through and make sure you actually understood where all these numbers came from. Feel free to stop me if I said something you don't understand. All right, that's what I calculated as well. So my final answer, I'll put a box around this, is going to be anywhere from 0.58 to 0.769. And what this means is if this is my sample result right here, notice that scatter plot's already given. The true population might be slightly steeper sloped, slightly less sloped, you know. And so there's this kind of range of possible values for the slope, and we don't know what it is, but we are 90% confident that for every point that someone scores in verbal, they're going to get somewhere between 0.58 and 0.769 points in math. Predicted. So again, a good point to pause and ask if there are any questions. Okay, no questions are forthcoming right now. Okay, so if we look at this one, notice that this has less of a printout, but it has everything that we need. So let me just try this, and let's not worry about doing the entire thing. Maybe we'll, but let me do this. So with that, I want to see if you guys can plug in the values. I'm just going to put the plus or minus right here. Fill in these values based on the data that you see here and come up with what the appropriate numbers to be filled in will be. Now, does it give us a confidence level? It doesn't. So let's say that we're going with a 95% confidence level. So see if you can fill in all of that.